In today's video, we're going to discuss the concept of torque. So looking back on the semester, sort of what we've done is we started with kinematics, which was just how do we describe motion, position, velocity, acceleration, angular descriptions of motion with angular position, angular velocity, angular acceleration, all of those things, and developed a nice quantitative way of describing motion. From there, we moved on to dynamics, where we looked at Newton's laws and how forces affect motion. Essentially, forces cause accelerations and affect how objects move. Since then, we've been looking at conservation laws, and we've sort of developed, we've looked at two major ones. We've looked at the concept of energy and how energy is conserved within a system unless there's some external forces that are causing that are doing work on that system, or if that system is doing work on the environment that would change the total energy. And more recently, we looked at the idea of momentum and how if we have momentum's conserved in collisions, or if there's no external forces doing any impulse on a system, the momentum of that system is going to be conserved. One of the things we looked at when we were doing energy, though, is we went beyond our particle model. Everything else was within this particle model, where we took a complex object and essentially just imagined it as a single particle with a given position, velocity, acceleration, all of those things, and we were analyzing it with that model. When we looked at energy, we expanded that into, some weird shape here, a rigid body model where we modeled objects as having a finite sort of spatial extent, a shape that didn't change as the object moved, and this allowed us to deal with the fact with rotation. If you have a bike tire, was the example we used, that was spinning, the particle model would say that that has no kinetic energy because it's not changing its position at all, but clearly there's masses moving when that object's spinning. And the rigid body model, the idea of moments of inertia and the kinetic energy of rotation, um, kind of fixed that, or made that model apply better to realistic situations where the particle model sort of failed a bit. What we're going to do now is we're going to revisit our concept of dynamics and how forces affect objects in this rigid body model sort of picture. And that's going to bring us to the concept of torque, right? So um, that's what we're going to look at today, torque. And we can think of torque conceptually as essentially when we apply forces, say you were to push with some force on this rigid body, it can not only move that object, but it can also start that object spinning or try to turn that object. Torque, you can loosely think of conceptually as how effective that force would be about at rotating that object, or getting that object to start spinning and speeding up how fast it's spinning. Um, so to do that, to kind of introduce conceptually the concept, I'm going to think, I like to pose this question in synchronous sessions, but it's a good thing just to get us thinking about what goes into torque. So think of, looking down, top down at a door. So this is our door, and you want to open that door, but so you can walk through it. Which of these forces, A, B, or C, is going to be most effective at getting that door to open? Right? This is something we've all experienced, trying to open a door. Where do you want to push on the door to do that? If you stop and you think about this, well, that all depends, right? And what does it depend on? It depends on where the hinge is, right? If the hinge is over here, then force A, pushing furthest from the door, is going to open it. If the hinge is here, it would be force C. But the gist is, it depends on where the hinge is, which brings up a very important point about torques. Torques depend on what they're pivoting about. Torques are applied about a point, which brings me to my favorite physics pun. But whenever we're discussing torques, always be sure what you're torquing about. But uh, but right, so whenever we define a torque or want to speak of torques, we have to be specific about what point we're pivoting about, or what that torque is applied about. All right. But once we've defined a point or a pivot or the point on that object that we're considering the torque about, then we can answer, all right, which force is going to be most effective at opening that door about that point. And in this case, hopefully we're all familiar with this, it's going to be C. The further you are from that pivot, the better that force is going to, or more effective that force is going to be at spinning that object around that pivot. So torques depend on where the pivot is. They depend on the distance the force is applied from the pivot. What about this? What if I apply those three forces all at the same point, but at different angles? Well, in this case, the most effective force is going to be force B. It's going to be the one that's perpendicular to that object, the distance between the pivot and where the force is applied, right? So torques also depend on the angle between the distance between the pivot and where the force is applied and the angle of the force. So putting this all together, what do we have conceptually? We have torques, essentially the effectiveness of a force at rotating an object, depend on obviously how hard you push, the magnitude of that force. They depend on the distance from where the pivot is to where the force is applied, and the angle between the direction of the force and the direction of that distance. Mathematically, it all comes down to this. We define torque as, we can calculate torque rather as RF sine phi, where R is, so if we look at this example of a wrench, R is we define a pivot, as we said. So in this case, we have a wrench attached to a nut. That nut is going to be the pivot point we want to define it as. If we apply a force at the end on the handle of that wrench, we apply this force in that direction, the torque can be calculated as R, the distance between the pivot and where the force is applied. Here, I'll switch colors. R is going to be the distance between the pivot and where the force is applied. F is the magnitude of the force that we're applying, and phi is the angle between those two vectors, the R and the F vector. And that gives us our numerical value of torque. Sticking with our sort of notation that we've gone through the whole semester, torque is referring to sort of a rotational type property. Its symbol is the Greek letter tau. Its units are Newton meter, forces in newtons, R is in meter, sine of an angle is dimensionless. Another thing about torques that we have to pay attention to is they have a sign, right? So we're going to go back to the convention of our angular description of motion, where counterclockwise is positive and clockwise is negative. So if we're thinking about that wrench again, and we have all of these forces, applying torques, forces that are trying to rotate it counterclockwise in this direction are going to have torques greater than 0. So this force here would be trying to rotate it about this pivot counterclockwise. It would have a positive torque. Likewise, this one, it's still going to be trying to push it counterclockwise. These two forces here would both be trying to turn this wrench clockwise, so they would have a negative torque. These ones that are sort of along, pushing into or out of, towards or away from the pivot, actually have 0 torque, right? That angle sine of phi would be equal to 0 in those cases, because the angle would be 0 or 180. But key point, torque has a sign, and that's going to be very important, because just like with forces, when we were looking, we wanted to know how all the forces acting on an object influence how it's going to move. It's the same with torques. We have to, each force, so if we have some rigid body here, each force applies a torque about the point, a point on that object, And the net torque is what's going to determine how that object moves. Just like the net force determines how an object accelerates, the net torque is going to determine its angular acceleration. So we need to, we're going to need to consider that net torque. And, if I have one force that's trying to rotate it clockwise and another force that's trying to rotate it counterclockwise, um, they can perfectly cancel. The signs of which way they're trying to rotate that object matter. They can cancel each other out and not cause it to rotate, or they can add together and get it to start spinning and speeding up. Um, but again, we're going to be looking at the net torques, and those torques have signs. We use the convention counterclockwise positive, clockwise negative. The last thing that I kind of want to cover in today's thing is what exactly do torques do? And it's really analogous to Newton's second law, where we knew the net force is equal to mass times acceleration, and this described the linear motion sort of the object, right? If you had some net force, it would cause it to accelerate. Torque is essentially the analog to that, right? The net torque causes an angular acceleration on that object, where it's equal to I, the moment of inertia, times the angular acceleration alpha. And these two equations are essentially Newton's second law. One dealing with linear motion, it's going to tell you how the object accelerates. One dealing with angular motion, how the angular acceleration changes. Mass, the heavier the object, the harder it is to accelerate it. It's sort of the inertial mass. The moment of inertia determines how hard it is to get that object spinning. If you have a big heavy wheel, it's going to have a large moment of inertia. You're going to have to apply a lot of torque to get it spinning. If you have a small light wheel, it's going to be much easier because it'd have a smaller moment of inertia. But that's the gist of what torques do. They cause angular accelerations. And we can now use that and add that to our rigid body model and get a fuller, more complete picture of how forces affect how objects move. To do so, we need to apply both our linear dynamics that we're familiar with, Newton's second law, where the force, mass, and acceleration are related, and the rotational sort of version of Newton's second law, where we have a torque, a moment of inertia, and an angular acceleration, and they're related through this Newton's second law. So let's do an example. All right, you have a pull start lawnmower, and the rope is wrapped around an axle that's essentially a disc of radius 0.25 meters. And for the engine to start, you need to apply a torque of 37.5 Newton meters about that axle. So part A, what force do you need to pull the rope with to start the engine, right? To do this, let's look at the problem. We essentially have, if I look at the disc, I have the disc I'm pulling about, it's got a rope on the edge. Sorry about that. And I'm pulling with some force tension on that rope, right? I need to figure out what the torque is. Well, I know I need to pull with the torque of 37.5 Newton meters. The question is, what force pulling on that rope will do that? Now, remember, we apply torques about a point. So in this case, there's an obvious point we're concerned with, the pivot at the center of that disc. And that force is being applied at r, the radius of that disc, and it's being applied at a right angle to that distance between where the force is applied and where the pivot is, right? So to figure this out, we know that we can calculate the torque due to that tension, or the force we're pulling with, as r f sine phi. And in this case, r, the distance between the pivot and where the force is applied, is just the radius of that disc. F is the tension I'm pulling with, right? It's the force we're trying to solve for. And the angle between those two vectors, are the distance between the pivot and the force, and F, the force, is 90 degrees, right, which is equal to 1. So this all just equals R times that tension. We can solve for that tension. It's equal to 37.5 Newton meters divided by the radius of 0.25 meters. The meters cancel. And this ends up being, if you enter it in your calculators or just do some long math, 150 newtons. So if you pull with 150 newtons, that's enough to start the lawnmower. The second question is, let's assume that there's a bearing at the start of this wheel, and that bearing isn't perfect, it's not frictionless or whatever. It also has to start, it's pulling on the engine and getting that moving. If we take all of that those forces that are going to be applied in addition to our rope from the engine, and we say that they apply a 10 Newton meter torque in the opposite direction that to the torque that we're applying with that tension, how fast does that axle get spinning if we apply that torque for 0.1 seconds, right? To do this part, so this was part A, to answer part B, it's a matter of, okay, we need to know how fast this is spinning. We're going to need a description of that motion. We're going to need essentially an angular acceleration. To get that, we're going to need to use Newton's second law for rotational motion. The net torque is equal to I alpha. If we look at the axle again and spinning, the net torque is the torque from all of those forces, which is going to be the torque due to the tension that we were thinking about in the first part of our problem, and it's also going to be the torque due to all the other stuff. I'll just put T sub 0, this 10 Newton meter torque in the opposite direction, right? If we think about that, we have to add them together, and we have to remember that the directions of these torques matter, right? So if I'm applying a torque of 37.5 Newton meters, and this torque from all the other stuff is in the opposite direction, it's going to be negative. It's going to have a negative 10 Newton meter torque on that. So I end up with a net torque of 27.5 Newton meters, right? That's going to be equal to the moment of inertia times alpha. Now, the moment of inertia was given in the problem. We could look up a disk on a table and, given the mass, calculate it, but I've just given it in this example. So if I want to know alpha, that angular acceleration, it's going to be my net torque divided by my moment of inertia, which is 27.5 Newton meters divided by 0.11 kilogram meters squared. If we run that through, that ends up being 250 radians per second squared, right? So Newton's second law again for rotation, once we know the net torque, gives us our angular acceleration. Now we can use this and our angular kinematics to determine how fast it's spinning after 0.1 second. So we know the final angular velocity is equal to the initial angular velocity plus the angular acceleration times delta t. Well, the engine wasn't spinning when we pulled it, so it started with 0 radians per second. And its angular acceleration, we just calculated to be 250 radians per second squared. We're pulling on that and applying that torque for 0.1 seconds. So this whole thing ends up being 25 radians per second is how fast we're spinning after pulling this for 0.1 second. And that starts the engine. But again, stepping back and looking at how we do this problem, a lot of these sort of rigid body problems with torques and that are going to be very similar to what we did when we were first doing dynamics, except for we have to sort of keep track of the things associated with rigid bodies, like where those forces are applied. Because not only are we going to end up applying F net equals ma, we're also going to have to apply Newton's second law for rotation, torque equals I alpha. And with those two things, we can figure out whatever we're going to need to figure out. All right, so we'll do more examples in our synchronous sessions. we'll go over some polling questions, all the usual stuff to make sure we're getting comfortable with this. If you have any questions, reach out to me, email me, or bring them up in our meetings, and I will see you then.